now. Hey everybody, so here we are, week 2 conservation of energy review. So this is just again review of what you learned hopefully during week 2. So if you were lost on anything, hopefully this will help to clear some things up. So we talked about the law of conservation of energy. There it is right there. Energy cannot be created or destroyed, only transformed from one type to another. Another way of saying that is the total energy of an isolated system remains constant. So we talk about a closed system or an isolated system. Could be all kinds of things. We could be talking about the universe, or just the earth, or just a little mechanical setup I might have here of, flinging things or whatever. So any of those could be a closed system. One good example we would use, definitely if we were in the classroom, we'd be talking about Newton's cradle here. You've all seen this before, and people, one of the most often asked questions is, why doesn't it keep going? Like as if that's what it's supposed to do, but it obviously doesn't because of the conservation of energy. So you grab one of these little balls on this side and you pull it back, and that's how much energy is in the system. However high you pull it back over here, there's no more than that. It's eventually going to run out. As they collide, it shares energy, and you can hear it. There's noise. There's probably a little bit of friction and heat produced in there. So eventually the energy winds down and it's out. If it would go forever, then we'd be solving the energy crisis, right? If we could actually put only that amount of energy in there and then it just keeps going, that'd be great. But things don't work that way. And so the energy is not destroyed. It's only changes form from one type to another, which is what we're going to talk about now. Here's another common example, or huge example, the nuclear power plant. We'll just briefly run through this here, but essentially we got these control rods of uranium that is essentially heating water. So there's nuclear fission happening there, splitting of atoms, and which releases that energy, and it really just heats the water up in a little steam generator. This is all in the containment structure here, and then the steam ultimately just spins a turbine. It's obviously a lot more complicated than all of that, but it boils down to, no pun intended there, it boils down to the fact that we're using the nuclear reactions there, decay, to boil water, and then that steam spins the turbine, and now we're just like an old-fashioned anything. If you get something spinning, you can run through the generator there and generate electricity. So it's really just a very modern steam engine, right? And it's carbon free. Okay, so what we're doing, we're converting the energy inside the atom then basically into steam and then into electricity, right? And we can only get out the amount of electricity that is in there, and then we'll lose some along the way, right, where we lose some heat. Okay, so the idea is to be as efficient as possible to not lose any of that energy. We may have done this in class. We'll just review this. The amount of energy in the universe tomorrow will be the same as the amount of energy in the universe today. True or false? By now you should know true for sure. The universe is a closed system, has a certain amount of energy. It doesn't lose any, it doesn't gain any, it just keeps changing form all the time. You may or may not have watched this in class. If we didn't, you can go and watch it. It's Walter Lewin's last lecture. So essentially what he did, this is him here. He's on a big stage actually, and he's got a bowling ball at his chin right there, and he's going to let it go, and it swings across the stage and then comes back, and everybody's afraid he's going to smash him in the face, right? And then obviously probably what happened, or what's going to happen here. Oh, nothing. Okay. So that'll happen every time, as long as you don't push that, as long as you just let it go with whatever energy you've got to pull back to. It cannot, because of the law of conservation of energy, it cannot go higher than where it started. Okay, so if we want to understand that a little bit more, this is essentially the bowling ball on a string here. Highest point there, and we'll look at it over here. So we'll talk about it in 5 steps. So he's got it pulled back right there. Max potential energy, right? It's all potential energy. So if it was just hanging, it would be right there at 3, we'll say. And then you pull it back, and that provides the energy. You are putting energy into it, pulling the ball back. No kinetic energy because it's not moving. And then as soon as you let it go, it starts to convert into kinetic energy immediately. And as it swings down at the bottom where it gets to where it would be hanging straight, notice no potential energy, and it's all kinetic energy. So all that is converted completely into kinetic energy right there. Halfway, it's equal, right? That's the equal point. So, and then on the way up the other side, it'll be just in reverse. Now they're equal again, and then it's back up there, max potential energy. And each time, because of friction up there, friction with the air, it's going to go less and less, right? It's losing energy along the way. So it's never going to go higher there or there than what you started with. Another way to look at this would be like a video game kind of thing. Here's position 1, or like a bar chart, right? If you can imagine like your energy levels going up and down, right, when you're winning and losing in a game. If the here we are at position 1, all potential energy, that should be 0. I couldn't get it to show up as a 0, so just as low as it can go because it's not moving, right? That's position 1. It's all potential energy. And then as you let it go to position 2, now they're even at that point. It's slowly converting. If you could imagine it in motion, the one goes down, the other one's coming up, and then we get down to the bottom at 3 here. No potential energy, right? We know there really is because it's hanging, but in terms of our system here, it would just be hanging and not falling anymore. So you provided the potential energy in pulling it up there, or he did in this case. And so all of that potential energy has run out, and it's converted all into kinetic energy, and now it's swinging back up the other side. It's just a repeat. They're equal again, and then at position 5, it's now back all to potential. That, if you can imagine that one point where it hits, swings up and kind of stops, as it's at that point, it's all potential energy, and it uses up the kinetic energy to get back up the other side, back and forth. Okay. Makes sense. So then, I don't know if we watched this in class either at this point, but what's wrong with this? So obviously you probably know. If I can pause it along the way. Among other things, so this is the exact same scenario we're talking about. He starts with it there. He might give it a little extra energy with a push, but it looks like he barely gets it off of there, so let's just say it's rolling. It cannot roll any higher than where it started. It only has that amount of energy to go, so there's no way it could go all the way up, right? Among other issues, but that's our main one there. Breaking the law, conservation of energy, which we should mention. So these are real laws. These are laws of nature, right? We've got laws like, you know, no speeding and don't run a red light and don't steal things, and you can break those laws and pay the consequences. But these are real laws of nature that just cannot be broken. You cannot break any of these laws. So anytime the questions asked, just keep that in mind, that these laws that we're going to be talking about always hold true. Okay, always. So here's a few formulas to go along with them that we probably did in class. We'll review them. Kinetic and gravitational over here. So here's kinetic energy, Ke, 1/2 the mass times the square of the velocity. And there's your variables down there. So when you run this equation, make sure you're taking half of the mass and then squaring the velocity and then multiplying those together. Don't take half of the whole thing. Don't square the whole thing. All right. If we want to calculate potential energy due to gravity, gravitational potential energy, it's just mass times gravity times height. That's all it is. Whatever your object is, the mass of it, how high it is. Off the ground is the h, and the g is the gravitational constant. So here on Earth, everything falls at the same speed, 9.8 meters per second squared. That's its acceleration. Doesn't matter what it is. That's how fast it'll accelerate towards the Earth. 9.8 meters per second per second. So every second that it falls, it'll increase another 9.8 meters per second. Okay, here on Earth. So when we do all of our equations, as far as I can remember, they're all going to be here on Earth. So we'll always use this 9.8 for that little g. Anytime you see the little g in an equation, it's a 9.8. Okay. Over here we've got elastic potential energy. 1/2 k times the square of x. So k is the spring constant, which will always be given to you, and that's always going to be different. It just depends on what we're talking about. Let's talk about a rubber band for a second. There's some spring constant for the rubber band, right? There's a spring constant for a metal ruler or for a spoon, okay, or a spring. You got a spring right there, okay. So we'll always give you that number. That's just the strength in the object itself. And then x is the spring displacement. So if we're talking in terms of the rubber band, the displacement is how far it's stretched, right? You got to put energy in there. It's easy, but it's not going to stretch on its own. You have to put the energy in there, and however far I pull it back, that's the spring displacement. And it should make sense, right? If I was snapping you with this, your arm, right, the farther I pull it back, the more it hurts. Or if I was just shooting something, right, if I put something in there and I wanted to shoot something across the room, a little slingshot kind of thing, the farther I pull back, I'm putting more energy in. I broke it. The farther I pull back, more energy, so the farther it's going to shoot, okay? So our total elastic potential energy then primarily comes from the spring displacement, how much energy you're actually putting into it. Gravitational potential energy, so really about how high something is lifted off the ground. So in this case here, this heavy container, the higher up it goes, the more potential energy it has, because you're fighting gravity, right? The higher up I lift this, I'm fighting Earth's gravity, so it takes a little bit more energy to get it up that high, okay? And the higher I go, the farther I am away from the Earth, the more energy I put into it to get it up there. Therefore, it has more potential energy the higher it is. So the height is important. So that's what this one is here. Potential energy due to gravity, which is usually how we say it'll be represented like that. Potential energy due to gravity, okay? Stored in an object because of its position relative to some other object. In this case here, these two rocks here, which one has more gravitational potential energy? A or B? Oh, very good. So we're going to go with A for several reasons. Assuming B is the same type of rock and it's not made of some extraordinary material that's really dense, right? What's the, I was trying to think of Captain America's shield. That's like some super metal stuff, right? Vibranium, is that it? If it's the same kind of stuff, then, and we can just look at the size. So obviously A has more mass, giving it more energy, and it's higher off the ground, right? So it's up there, adding to its gravitational potential energy. And we just kind of answered this. The three factors that will contribute to it, we know this because we just did the equation. Mass, gravity, and height. And so here's our equation again. Mass, gravity, height. The unit will be in joules. We'll talk more about that in a second. So when you do this equation, make sure always that the mass is in kilograms. This will always be your number for gravity, and that's always the unit. And then the height, make sure it's always in meters. That way your unit comes out in joules. Which, just here's a little explanation of what is a joule. So if you want to read through those, it's not that much. This one might make the most sense, the second bullet. Energy required to lift a medium-sized apple 1 meter off the surface of the earth. So imagine taking an apple and lifting it up 1 meter, right, about 39 inches off the ground. It required 1 joule of energy to do that, okay? So here's a practice problem. If a boulder has a mass of 595 kilograms resting at 128 meters up in the air there above the Earth's surface, rather. How much potential energy does it have? You should always write down your equation first. Great thing to do, mass, gravity, height. And then you just plug the numbers in, 595 times 9.8 times 128. And because of the fact, well, let's do this first. Students, so students always ask about units, and generally speaking, I always say, you can figure them out. The units are whatever was in the problem, and there they are. So if you were just doing this, the kilogram doesn't get erased. The meters per second squared doesn't get erased, and the meter doesn't get erased. So your unit really here is kilogram meter squared per second squared. And it just so happens that a kilogram meter squared per second squared is 1 joule. So as long as you do it in the right form with kilograms, meters per second squared, you'll always use that. And then this is in meters, it'll be in joules. And your answer can just be a J. Unit is important. If your answer that you give is 746,368, wrong, okay? Has to be a unit, always. We don't like naked answers, okay? So put a unit on there, always. Keep that in mind. Always show your units. Should probably always show your math work as well. Here's another one. For kinetic energy, or I should say, here's the equation: 1/2 the mass times the square of the velocity for an object in motion. Mass is always in kilograms. We can write it as kg. And then velocity will always be in meters per second. And in this case, it's squared, so it'll be meters squared per second squared. You don't really have to worry about that, okay? And then we got it'll be a joule again. So if we do a problem, if a bullet has a mass of 16.2 grams, travels at 253 meters per second, how much kinetic energy? Hopefully you realize that it's in grams, right? And we like our kinetic energy to be in kilograms. So the first thing you have to do is convert that into kilograms just by moving it 3 decimal places to the left, because there are 1,000 grams in a kilogram. So just move the decimal 3 to the left or divide by 1,000. And so you're squaring this number because of the fact that we're putting it into joules. You don't really have to, don't worry about squaring the units. It comes out to be kilogram meter squared per second squared, which is a joule. As long as you start with the right units, the answer is going to be in joules. Lastly, 1/2 k times the square of x for our elastic potential energy stored in an object. Here, pulling a rubber band, just like I was when I broke it. Okay. So k is the spring constant, x is the distance stretched or pulled back or squeezed down, whatever it might be, okay? In this case, of a rubber band with a spring constant of 88 kilograms per second squared is stretched 7.5 centimeters. So its potential energy. Write down the equation. There you go. We want this in meters, so you're just converting that into meters. There's 100 centimeters in a meter, so you're moving the decimal point 2 to the left, or dividing by 100. And then there's our answer, 0.25 joules. Okay? So, how are these different forms of energy related? If we look at this right here, this is really summing up everything we've been talking about here. If we're starting at A, this little roller coaster has some amount of potential energy because it's up there. When it gets down to C, it's going to have the same amount of energy, but now it's kinetic, because it's all converted into kinetic energy. So some things that we're ignoring is the fact that it's going to lose energy on the way. It's going to make noise. There's going to be friction and heat loss with the track. All those kinds of things that, if this was a full-on physics class, that we would have to account for, and we're just going to sort of skip over those kinds of things. So potential energy due to gravity is equal to the kinetic energy at the bottom, okay? And then here it gets about halfway back up, and so they would be equal right there, okay? The real point here is, because we're just understanding concepts, is that it can't have more kinetic energy there than the potential energy that it started with. That's important, okay? over here, the same thing is true. Pull back this bow, give it some amount of potential energy, and then you let it go, and it immediately converts into kinetic energy, equal amount. It can't have more than what you started with. Okay? Impossible. So, where it all culminated was in class, what we would have done if we were there. We did this little marshmallow lab, right, like this, where we had a spoon. Marshmallow, I actually have raisins here, right? And we're bending them back and flinging them up into the air, right? Putting them on the table. Oh, yeah. Got a little drawing here. Can you see that? So there's our table. Spoon sticking off the end of the table where you could put the marshmallow in there. We're going to flick it up into the air, and there'd be a ruler there. Somebody would watch how high the marshmallow goes, okay? And so by doing that, we can figure out a lot of things. We don't know the spring constant of the spoon, so how we're getting to that is by however high it goes, right? We flick this marshmallow up into the air, okay? And somebody watches how high it goes, and so when it gets up to its highest point, we can measure the gravitational potential energy there because we know the mass of it, we know what gravity is, we know how high it was, okay? And once we know that, that's the total amount of energy, right? Because if you think about it, what we kept track of, I mean, you probably did this a different way in class, maybe with a little spring simulation. There was 3 different trials where you'd pull it down like that, and then you'd pull down farther, and you'd pull down even farther, and we know what happens, right? The farther that you pull it down, the higher it's going to shoot up into the air, okay? And so we'd have 3 different types of amounts of energy based on how far you pulled it down. And so go 3 different heights, and then we can just very easily, once we have gravitational potential energy, that's equal to the kinetic energy. And once we know that, and we know the mass of it, we could calculate the velocity at which it was moving. But we can certainly then, because we know that the gravitational potential energy at its highest point was directly related to how far down you pulled the spoon and how much energy you put into the bottom. So the number for gravitational potential energy would be equal to the number for elastic potential energy. And then we could measure the displacement there, and we could figure out the spring constant for the spoon, okay? Overall, the ultimate point was that all 3 of these energies are equal to each other, because in this little closed system of a spoon launching a marshmallow, there's no more energy put in, right? We put the marshmallow on the spoon. However far back you pull the spoon, that's the energy that's in there. And as soon as you let go of it, and as soon as the marshmallow has left, that's it. It's not going to go any faster than that. From there, you're fighting gravity the whole way, and then it's going to get a certain height because of the energy that you put in, and then we can calculate all the rest from there, okay? So hopefully we got to do something in class that resembled that, some kind of a simulation thing, to highlight the types of energy, okay? So hopefully that was helpful. Hopefully it made sense a little more if you were confused on some of that. If not, send an email, we can talk about some things, okay?